think organizers were a chance to think about some of our work in kind of understanding and determining mold structure and talk about its impact. I'm going to focus on perovskite, but in this sense, they have so I'm breaking the talk up into kind of two parts. The first is kind of like tutorial level, the talk about mold structure and how we go about measuring mold structure. And then I'll talk about the specific application of this method, the two category methods that we kind of use in the like perovskite. So this work was kind of done by three of the postdocs, both within my group. So Nick Whittock to you, Ty Sterling also to physics, and then George to be detailed with Stanford. But then Peter and one of the brothers has really helped with the kind of instrumentation aspect of this. And then the funding and then some of the choice energy material research. So what I want to do now is talk a little bit about what I mean and how we go about programming. So I'm going to do this with kind of a simple example. So on the left side, that is the fictitious lattice. I've replaced it, and you can imagine that the blue represents atoms, and then I replaced I think 20% of the blue atoms by MHPs in a completely random fashion. So these are now kind of shown randomly, but about 20% density of the oxygen. And then on the right side, we're allowed to be clusters. So there's some probability there's a vacancy that there's another one that is vacancy. And you can pretty clearly see just by looking at the structure, if you want to think about this in terms of atoms, but completely different. So the question then becomes, how do we go about it? Quantify this, because it's not looking at extrapolation, to expect that whatever physical properties are, random states are going to be dramatically different than if you have these problems. Again, this is just a simple thing. Everybody here, I think, scattering is a good fast, except to point out that the premier method of doing this kind of for last and years has been, Bragg. And so pick up and then just have a method, it's very practice, and then the intensity, and then and go. So this is now basically an example of what we get in these two different scenarios. On the left side is for the vacancies, on the right side is the different clusters. You don't have to be too careful to see that these are just exactly the same. And I'm sure you all think of you can take something out of it. So, two things that will find out the difference in the structural scan out of the same variable. So what do we do? Basically blow up the scale. So basically what I'm going to do now is to say the diffraction patterns are not focusing on practice, but focusing now on the diffuse scattering. The scattering in between the practices if you want to think about it. And so if you look on the left side, the random vacancy case, we see this kind of bombs. Instead of more or less about origin, which is due to kind of individual atoms. We have to make random. And then on the right side, we see kind of two things. You see kind of the dots here, which are not the Bragg ones, but scattered in multiple here, the Bragg ones. And that's due to kind of these smallest regions where you can place it in kind of a cluster. And then we also see, kind of faintly these kind of different rocks and actually what would be the Bragg point. And those are then due to kind of these longer kind of rod-like features we need to dimension that either run this way or run that way. And the scattering are particular direction. So the diffuse scattering, and then this is slightly different. This allows us now to distinguish the so I treated this, at least in the previous example, as kind of static, and some of these small time scales things are not moving. And again, I think people in this audience understand that if the local order is dynamic and moving on a time scale, you can basically use neutron scatters, diffusion neutron scatters, they can be able to distinguish this. So how do we measure this? This method actually been around time. I don't have it in this talk, but I think it dates back to maybe the 40s or so. What has happened recently, both on the vector side and the neutron side, is we've kind of been a step change in our ability to kind of measure. And so if I think about an X-ray experiment, the kind of three pieces, there's the source, there's the detector, and then there's the sample. I've done most of my career in terms of X-rays and thinking about the blind dot dramatically in terms of sort of brightness. Similar things, although less significantly for neutrons. And so that's really helped to enable our ability to measure the scattering. I think more important than the X-ray side, over the past 10 years, the wide very large area data. And this now has enabled us to data X-ray side. What used to literally take weeks now can be done in 30 minutes from the X-ray side. Similar thing both from the neutron perspective, but now you're not several hours, but this still is significant. Often the challenge, the dominant challenge now is in this space, actually being able, in some cases, to throw adequately large things crystals for the neutron side. The X-ray side is a tiny number of microns and the data are pretty low. Crystals. Many of X-ray structures are going to upgrade in the whole their expectation is we can start to push things down to 10 microns, which I think will start to enable a lot more effective these kinds of measures. Okay, so I very briefly talked, gave you what hopefully kind of the tutorial, where it is, and now I want to focus the rest of the talk on the metal perovskite. And to join you, you can use some type of the recent work that we've done at the table. So you all know what perovskite structures. I'm going to tell you this. What different kind of the halide perovskite, like the oxygen, light, and single-valent halide. The structure you all know is from here. And so as I said, the X site sits in the halide, and then the 2+ ion that sits in the center. Typically, that's lead, although other kinds of materials you can. I'm going to focus primarily on that. Because halides are big, the atom of the molecule that sits in the A site, they also have to be big. It typically needs to consist of kind of small organic ions. The conventional case is methyl ammonium ion, which is kind of over here. Same thing as also, there are a number of other kinds of small organic molecular ions. Over, let's say, 15 years now, these have become very interesting from the photovoltaic perspective, and you're now getting kind of very high solar energy, kind of electric power and energy efficiency. They are approaching silicon. The conventional systems have silicon solar cells. They're starting to approach that now. The other big advantage that they have is that there's fusion process. So rather than kind of this like silicon, if you need it for very low processing temperature, at least in principle, you can now coat these materials onto some specific parts of whatever the substrate is using very in principle environmental design, low energy cost methods. So anyway, this has resulted in a tremendous amount of photovoltaic in terms of kind of understanding the property relationship in these. And that's what I'm going to tell you, but now in structure, I don't so we're going to focus this part of the our interest at the higher temperature phases, but in the cubic phases for both methyl ammonium lead bromide and methyl ammonium lead iodide. Methyl ammonium lead bromide and lead iodide. So we're going to focus in the cubic phase, they both undergo transitions, somewhere around the long room temperature, somewhere below room temperature. We can do kind of the globally average tetrahedral. So the question we're going to ask is, what is the dynamic local structure of both of these compounds in the cube? And the point I was trying to make before is that when I show you these kinds of structures, every kind of structure, in textbook with so-called important to keep in mind, local elements, ignore kind of the local aspects of this, and in fact, the dynamics. So as I said, we have taken kind of the solar community, kind of like storm over the last 15 years. And it's been pretty well established that if you compare these to the kind of conventional semiconductors, so they're gallium arsenide, there's a lot of defects in the lattice very soft. It's very, because you have soft, the elastic functions are very low. And then, not surprisingly, you also have a lot of antimonic effects. And a couple of consequences of this, the work down here with Peter, is that the photon lifetimes are extremely short. Yeah, here's a map kind of the acoustic photon lifetime. And you can see, by the time you get out to the real zone, we're hoping out picoseconds, about the same kind of thing as the lattice vibration. There's also a very strong coupling between the electrons and the photons, and it's speculated that this gives rise to the favorable TV properties. So these are kind of, that's kind of good. One of the bad things about this is that they're big conductors. It's not really something you want in the solar cell. You have the science and kind of the microns that are mobile. And so, understanding the ion migration is something that's really important to enable us. So I'm going to show you now a couple of different scattering maps of these particular compounds that we've done. And I should mention that these are all deuterated, so they're fully deuterated organic. So this is now a map of the bromide compound is produced with a single crystal. So the top is X-rays, the bottom is neutrons. And these are then halfway between Bragg points. So if this is the halfway cubic, so it doesn't really matter which direction we're going into. This is L half, or 1/2, 1.5, and 2.5. This is the X-ray diffuse scattering, and this is the neutron diffuse scattering. And there are a couple things that are kind of prominent here. We see kind of intense, usually intense points about halfway, about half position. And then perhaps right then we see these strong rods scattering that probably most easily here as well as here. In the X-ray case, these are more or less kind of uniform as you go across this. And then if we look down in the neutron case, we also see these kinds of the rods, except now they're not really uniform, right? We have these that are intense, less intense, more intense. So you kind of pick out this kind of distinct rod, kind of rod-like, square-like region, both in the X-ray case as well as in the neutron case. So this is true for the bromide compound. This is just above the trend. This is just into the kind of the cubic phase. We can also look in the iodide case, like this was shown here. It's an iodide, we still do the same thing. On the top is X-ray and neutron. You see kind of similar features that talked about before, kind of the bright dots at the half position, and when they draw up. But on the right side now, I'm showing you some results of MD simulations. So results of MD simulations that I'll discuss a little bit later, that was done by and if you look at the MD simulations that compare them to the X-ray diffuse scattering, you actually see really good. Almost all of the features I kind of discussed, you see these broad features really well, and you see they're more brighter spots that have position. And then if we look down here to the neutron case, and we saw these kind of alternated pattern before, that's pretty well manifested as well. So what I'm going to do now is to use the results of both that get used in both X-ray and neutron scattering to start to draw some conclusions about the nature of the way these local correlations happen. And I should also note that aspects of this have also been observed in the cesium compound 2 years ago, where they see kind of these very similar rod-like features. So let's start by, if we look at kind of the diffraction pattern, and we start here, we're starting at the scattering pattern. We look first at kind of these half positions. This is kind of similar to the so-called central peak phenomenon in the oxide perovskite. We say very similar behaviors, and our interpretation then of this is that even into the cubic average structure, you have more static kind of waves or bubbles of the lower symmetry tetrahedral. And there some of the time here, and we can kind of assess the things on the order of 30 or 40 picoseconds back. And so these are kind of the static bubbles that they do brought up for this. They're reasonably look at the number of the. If we look now at kind of these rods, you see a rod scattering between kind of two phase that corresponds to the sheet or a plane that's on some kind of local structure in real space. These occur at half position for the dominant cell. So what happens is that you have these local regions where kind of the heat in the prospect that it's so you have this kind of correlated anti-phase tilting. And that's kind of shown here. So this is now the actual cubic average structure, and you can see now we have this kind of rotation to the positive sense and then the negative sense if it rises to the normally structure. So what I want to do now is show you kind of a picture of what we see using the MHPs design. So what I'm showing you here now is one cut in one plane in real space where each of the octahedra, so each of these octahedra is color coded in the sense of what is the rotation. And so let's imagine that the negative sense this direction has color coded in the red, or the different color more red, larger rotation angle. And then in blue is kind of the opposite. That's something more positive. Where again, the bluer it is, the larger the rotation. And so if you look here, we see the kind of checkerboard region where we have an alternating blue, red, and red that extend a few or five kind of units of the crossing zone now in latitude. One of these is the cell. So we see kind of regions, one over here, and other ones over here. And then we have these regions that are significant where there are planes, they're kind of significantly small. So this is one cut in three-dimensional structure. I take that same cut and look on the side. That's from here. So over here. So this is where this specific line is. So if we look, we now see that this particular region actually corresponds to kind of what we just in the more opposite direction. And you can see it doesn't appear here, but below this you also see kind of alternating checkerboard like that. So what we conclude from this is that we have local regions of several communities with cells across, where you have this local tetrahedral structure that's embedded in this local average cubic. And of course, these run because of cubic symmetry, they can run in any of the three equivalent crystallographic directions. So as I said, we see these 2D sheets of the disc or pancakes of these rotated octahedra. What I'm going to show you now is this much fluctuating on the so that means in the neutron scattering, we look at the points. Basically, we see resolution limited line shape that tells us that we can measure these are more or less static. If we look at kind of the scattering, if we energy result of the scattering about the rod, so here's some region that has integrated the intensity in the plot as opposed to energy transfer. We can kind of fit that as a little bit broader than the resolution, and we end up with an experimental list that's kind of listed here corresponding to like picosecond. We can basically do the same thing, or they can be. And that's going down here, and we're getting a little bit longer about picoseconds or so. But anyway, what we conclude from this data is that spectrometer domains have lifetime somewhere around the 84 picoseconds. And we can that gives lifetime, we can get it directly from the data, get kind of the length scales and play looking at the widths, either across the rod or along the rods. We look across the rods, we kind of see diameters of the fluctuating machines on the order of about 3 or 4 nanometers, then we're going to go across. And then orthogonal to that is more or less 1 unit cell consistent with this kind of structure that I talked about. And summarizing. So one of the questions that arises is how much of this is thermal? How much of this is thermal? And so kind of a different study, we actually use X-axis to look at kind of what the bond length disorder is of temperature. And you can plot that and extract basically Dubai temperatures from that. And then you can also get a sense of room temperature somewhere over here. What fraction is kind of thermally driven, what fraction is static. And in fact, the conclusion is that almost all of this is thermally driven. Skip that. So if I'm going to summarize this, globally, what we see is this kind of cubic kind of structure. At the time of the structure is something from the Bragg diffraction. Locally, we see this kind of more. We see these kind of small tetragonal regime. This has been a movie where the time space is about 50 picoseconds. It's showing you the fluctuating nature of the 3D domains. And if you look carefully, you can kind of see them pop into the distance, the round, and then disappear. So that when I mean structure property relationship, this is kind of how we're going to think about this. This is the time and talk a little bit about this. Okay, it's great. I thought about the structure, the light, so if we just think about this from the ion connectivity standpoint, a lot of the simulations that have been done with kind of estimating ion properties on all three global infrastructure. The lifetime of the pancakes is larger than the temp frequency. So if there is some fraction of these black and not being in the cubic phase, they'll be in that fraction. And so this is something that, going about modeling, you kind of have to think of. And then, again, we don't really know. This has a significant impact on this. We also kind of had the locally oriented regions, so it's like carriers and curves, they see this kind of dynamic. Fluctuating, spatially fluctuating graders in landscape that then have to go ahead and I didn't really have a chance to talk about this, but there seems to be some local correlations that kind of the organic, which potentially gives rise to either local ferroelectricity or MHPs. And then just computationally, these domains are several diameters across. If you're going to be doing simulations, you have to account for that as a box size, and that data has to be big. Okay, so to summarize, I wanted to give you a sense of the importance of both larger global kind of general phenomena. And then I talked a lot about the local area and the Halide Perovskite and why it would be important. I do think that this is going to be an important kind of measurement capability going forward. It can have potentially a significant impact on kind of. And so last, just thank you for the work. Really was going here. There's what's been shown over there, kind of in the back. And thanks for your attention. I'll happily take any questions.
Thank you.
Welcome to class. Yesterday I told you exactly the way to model this. I'm sorry. Yesterday I told you exactly how to calculate the energy landscape. Okay. It's the different equations. The difference is we have to take the combination of the activity to the fact that we get a statistical which shows the.
Oh, okay. So I
we're going to try to discuss that more deeply. Yeah. That's fantastic. Thank you.
Oftentimes that is one of those values. the model, the great PC part.
You can ask me. So, how can you make a movie in realism?
So the movie comes from the ending.
Ah, okay.
Right, and yeah, so we all, I love to get the right. Well, actually, the principle, we use something like, actually, goes on for relations. And do this on the real time. Principle is considered, the obvious challenge is like, the more we able to keep this on people think time there. And we are going to do this now, and keep that about it. But I need to put it in file. It's more than.
I was the same as me. I mean, it's not embarrassing. We're both in different space in these indeed.
Yeah. So all, yeah, I'm right. All of the real estate conditions come from them. You just get for like 2 years out of it and time scale. But those agree pretty well with, what comes out of them. It's really possible to get them to impact and make it.
So there are any ways we follow, as like information from your interaction,
That's the best we come what I said here, but yeah, that's the best.
Thank you very much for your talk. You mentioned in passing in the slide that you saw indications of electricity.
Yeah.
Just very much curious to know.
Okay, well, not that we used to do, we're inferring the Ferroelectrics. What we see is if you, and again, I don't, unfortunately, I didn't leave time to go through this, but if you use the ND, you could turn off the scattering assumptions from the inorganic subatoms, just look at the organic subatoms. There seems to be 2 contributions to that, and one is kind of isotopic, which is really things that are correlated. And then we also, it's kind of hard to see here, we also see this lot-like structure as well, which suggests that there are the specific cases of organic life, and as you expand more of these pancakes, a little bit more than just one itself, and have to so separate from itself. So there seems to be an indication of some, local dynamic orientation of the anode, which has a 55 at the moment. So we go this way or this way, it suggests it is possible to electricity. I don't remember what it was supposed to be discussing. Then I'm not going to comment on whether that's the case, but we definitely see correlations would potentially give rise.
Great, yeah, I really think we're really interested in that, and so I think we can go on this. So, yes.
Thanks for your talk. So one thing from Carnegie. So it seems like there's 2 effects, maybe. There's like an energy width, which is like a lifetime, and a Q width, which is like a real space. Now with X-ray, you can get both of those.
We only get the Q from the dynamic of the.
But you have that information also there.
That came from the neutron.
Yeah, okay.
So that is a neutron connected with.
Right.
One last question.
Anyways, it was I have a question about the warranty instead. But do you use another method to see it, like TPM or?
There's been some work that's been done. So there are a couple of challenges with it. One is the dynamic to watch out everything instead of using what you can. Kind of fail. And then there's one green damage, and using green damage as well, but there's no green damage in the TPM interacting with organic. So here, this is not, then you consider kind of, there's been huge valuable work, but not valuable for this particular one. I mean, we were using very high temperature. The principle is not what the energy that we work with.
Do it style of for the emergency.
Well, the last is stop, right? And so there's not, the energetic landscape, anytime you really, right? So anytime you get usable energy, things are gonna be moving around. There's a tendency to go lower into the form of this diagram. So domain is very complicated, kind of the process, right? So the speculation, the truth is that you have them to have this fluctuation. Why does it need high? There are the 2D versions which can make them layer compounds for the process sheet. They make sandwiches which is more organic. That would beg the question, what does the fluctuation look like there? You have limited. That may give them the message. They don't go necessarily the training.
Thank you very much for the interesting discussion. Now, the second part, we begin by